Alright, hello everybody. This is my first time actually recording on my iPad, so please forgive me if I make any embarrassing mistakes. We're going to start off with our midterm. I'm going to try to break it down into probably just one page at a time. So in this video, we're going to go over problems 1 through 5. So if we look at number 1, we have to find the holes, the horizontal asymptote, if it exists, and the domain. We never use the word hole in our class. Instead, we called that the discontinuity. So please don't let that confuse you. It looks like a couple of us marked on Friday that we were confused about this problem. So let's take a look at this. Remember, I said hole equals discontinuity. So to start off with this problem, we could jump right to graphing. But to kind of understand it better, we can break it down and try to factor both the top and then factor the bottom. So if we look at the top, we can factor it. We can take a -4 out of both terms. So we get -4 times the quantity of x plus 4. Then in the denominator, we would get x plus 4 and then x minus 4. As we can see here, we have x plus 4 and x plus 4 on the bottom. So we can cancel that out. Remember, whenever we're canceling in a rational function, if we take anything out of the bottom, what was there still has an influence in our final graph, even if we don't plug that in. So now when we get this, we still, we could use this to help us, but it's probably easiest just to use a graphing calculator, which I'll show us in a second. But let's just try to sketch it real quick. Our parent function for rationals, I'll try to change the color. Our parent function will look, as I'm drawing in the tiny one, like that, but we do have some transformations here. So since we do x minus 4, that's actually going to move it over to the right 4, and then that -4 on the top is actually going to be, if we wanted to draw it just a little bit more familiar, that was odd, we'd have x minus 4 on the bottom like this. So it looks a little bit more familiar, a little bit more like a transformation. That means we would move over to the right 4, and then we would vertically stretch out 4 and reflect across the x-axis. So we would get a graph that kind of looks like this. And now we can check. I'm going to move over to Desmo so that way you don't have to look at a video of my graphing calculator. And actually already have it graphed here. I graphed the original function, and we can see our graph here. We can see our vertical asymptote. I can't do anything on here to actually show what I'm pointing at, but we can see that at x equals 4 there should be a dotted line. Maybe I'll do that. I'll graph real quick that vertical asymptote. There we go. And then we can graph the horizontal asymptote as y equals 0. So we can see those asymptotes on our graph, and we can kind of see that it's stretched out because we really do have right here where I'm putting the point, that is that original point that should be at 3, 1, but since we stretched it, it's at 3, 4 now. So if we go back to our problem, let's actually finish this up. Alright, so we have to find the holes, horizontal asymptotes, and domain. Let's just start with our horizontal asymptote since we already were talking about it. So that's my abbreviation. We're tempted to write it as just y equals, and in this case it was 0. But we really should write it as a limit, so that would be the limit as x goes to positive infinity, our function goes to 0, and the limit of x goes to negative infinity, our function goes to 0. So for the other two parts, I have to start a new page, but we are going to look for discontinuities and our domain. So discontinuities in our graph, we don't see any. But remember, we had, it was -4, x plus 4, and then x plus 4 times x minus 4 on the bottom. We can't have either 4, negative 4, or 4 on the bottom of our function. So these will be our discontinuities. We can't have x negative 4 and x positive 4. We didn't really see that in the graph because here there is a jump discontinuity, and on the other one, that's the one that we saw, and remember we call that an infinite discontinuity. Alright, and then for our domain, if we go back and look at our graph, it'll look like we're just not having an issue, only having an issue at that 4, but we are still having an issue at negative 4. So when we write our domain, it's going to be easiest to write it in interval notation, and that's how it's going to look on the multiple choice section of this test. So we're going to go from negative infinity to negative 4, union negative 4 to 4, union 4 to positive infinity. So here we had to use our parentheses on the 4s and the negative 4s because those points are included because those are discontinuities, aka our holes. So that one was a really long problem, and on the test this might just be one multiple choice question. So there might be a lot of work for one problem, but then some of our other problems aren't too long. So like if we look at number 2, we have this cubic function. We want to find all the relative extrema. The way that we did this in class, we just graphed it real quick. So let's go back to Desmos and graph this and just use that graph to check for local extrema. So on our test, you won't be allowed to use Desmos, so make sure you are familiar with using your graphing calculator here. We have negative x to the power of 3, and then plus 3x squared and plus 3. So here's our graph. Lucky for us, Desmos is pretty nice and gives us kind of what it looks like. If we did graph this in our graphing calculator, our standard window should capture this, and we could use our table to try to figure this out. But we do see a local extrema at 0, 3, and at 2, 7. So when we're doing this, we usually only care about the y value for our local extrema. So let's go back to our study guide and actually do some notes. So we had a local extrema at 2, 3, and that was a min. And then we also had another one, and I already forgot it, a max at 2, 7. Sorry. And this one was at 0, 3, not 0, 2. Alright, so that's how we would write it in class, but we might also see it as min at x equals 0 of y equals 3, and a max at x equals 2 of y equals 7. Those are our two different ways of seeing the answer to this problem. Please be familiar with both. And we just graphed it real quick. We should be able to graph that in our calculator as well. Once we move on to number 3, we're using our graphing calculator to approximate the open intervals where each function is increasing or decreasing. Again, we're just using our graphing calculator. We don't quite have the math yet that will come in calculus for doing this. So let's go back to our graphing calculator and let's plug it in. So we have y equals x to the power of 3 minus 4x squared plus 3. Alright, so now if we look at our graph, we can kind of see our normal cubic function. And we can definitely see where it's increasing and decreasing. We will need to know the points, our relative extrema here. And we happen to have a messy decimal for one of our values. But we should be familiar with that, and that's 2 2/3. So we can use that pretty easily for our intervals. So let's go back. I'm going to try my best to memorize this. Alright. So we have increasing and decreasing in that graph. We start off with increasing, so we start off at the left, which is negative infinity, and we went to 0, and then we picked back up. Remember, we never include the actual extrema in our increasing, decreasing intervals, and we picked up at 2 2/3, which would be 8/3, and then we went to positive infinity for increasing, which means decreasing, we're at the space in between, which is from 0 to 8/3, and that would be our decreasing interval. So that would be our answer for number 3. I'm actually going to cut the video here because I know I've been talking so long, and I'll pick back up in the next video at number 4.